Okay, time for chapter 18. Let's give you an idea about what stars are made out of, how that relates to the mass, the diameters of stars, and how we put it all together with the HR diagram. Okay, so most of the stars we can't see with our eye. They're too dim to see. The closest stars are all we can really see. We can't see beyond that in the night sky. You can only see 3,000 to 5,000 stars on a given night. Okay, and yeah, this is the number of stars within about 20 light years of the sun. There's about 100,000 light years across, so it gives you an idea of the closest stars here. Excuse me. Most of the stars in our local area are type M. Excuse me. Goodness. So not very many very bright stars, O, B, A, F, G, and then got a couple like the sun, K, mostly dimmer, some white dwarfs, which have already gone through their cycles, and a bunch of brown dwarfs too. So that gives you just an idea of, in our local area, what the sort of census is on the types of stars in this neighborhood. Okay, so here's a picture. If all the stars were brought to the same distance away from us, what they would all look like. So you can see the sun would be a little white dot there. And you got all these other little tiny brown dwarfs and class M stars. Okay, just because a star is bright in the sky doesn't mean it's close. It could be very bright and far away, or kind of dim and close, and they might have the same apparent magnitude, okay? This is pretty cool. This is a picture of Alpha Centauri and Proxima Centauri. Proxima Centauri is down here at that arrow, and here it is zoomed in there. This little tiny dot right there in the middle of that is Proxima Centauri. Now if you zoom, so Proxima Centauri is thought to be orbiting Alpha Centauri A and B, and if you zoom in on Alpha Centauri, you actually see that it's a double star system. And there's two stars that make up Alpha Centauri, A and B. Okay, so there's Proxima Centauri, and then Alpha Centauri A and B, and let's see, yeah, okay. So anyway, we can measure the masses of stars by looking at binary star systems. So you can see there's two stars here orbiting each other, and as they orbit around, we can use Kepler's laws to figure out their masses. So binary stars are one of the easiest ways to measure the masses of the stars. And there's another type of binary, which is spectroscopic binary. So this would be called a visible binary because you can actually see the stars. There's two separate stars here. And then a spectroscopic binary is your light is missing, and your light is missing. This is absorption spectrum, and you can see the as the stars move around, their emission lines are shifted because of the motions of them. So you get your Doppler shift, your redshift and blue shift that separates them. So that helps you determine their motions, and this is another plot of that, just showing their velocities changing over time, and allows you to, by that, get Kepler's laws. And this is Kepler's law here, third law. The p squared is related to the semi-major axis of the orbit, or the radius of the orbit. And you can solve for the masses of the stars then, M1 and M2. So this is Kepler's third law. That's what it looks like in a mathematical form. But just by getting the period and the distance, you can determine the masses of the stars that are involved here. Okay. Blah, blah, blah. Okay, what you can see is that the when we start plotting the brightness of a sun versus its mass, we see that there's a nice linear relationship. That means a higher mass star is brighter. As we go to higher masses, we get more and more light. So that's the first sort of hint that we can maybe find some relationship. So the brighter the star, the heavier it must be. And that's related because the bigger the star is, the more mass it has, the more mass it has, the more gravity it has, the more gravity it has, the more pressure it has, the more pressure it has, the more fusion that takes place, the more fusion, the brighter the star. Okay, so diameters of stars. You can figure out the diameter of a star by looking at its light curve. So in point 1, this star is about to go behind the star. When it goes behind the star, the light dips down. As it goes in front of the star, it dips down again, but a little bit less, because it's emitting its own light. So it will block out some of the light, but emit its own, so it's not as deep. And so by looking at that, this is basically watching this orbit in a single day. This curve would actually continue on, and then you would know by watching it go over and over and over again and loop continuously that something is orbiting a star like that. So these light curves allow us to figure out the diameter of a star by how long it takes to go around, and so on. So again, as a star moves in front of the other star, it's going to change the brightness that we see from the star, and that's called the light curve. And this is called an eclipsing binary, and that's when the two stars, binary star system, which means one star is orbiting the other star, but it's edge on, so we're looking at it as it orbits, so it blocks it perfectly in line with our, because you can think about it, a star could be here, and another star could be there. It could be orbiting like this, it could be orbiting like that, it could be orbiting like this, but the ones that are orbiting right edge on, so we don't see them at an angle, those are the best to get the most precise measurements. Okay, so putting it all together, we can figure out the surface temperature of a star, its chemical composition from its spectrum, its brightness, its radial velocity using the Doppler shift, rotation, mass, diameter. When we put all this together, we find this relationship between the stars. And the most important thing is the luminosity of a star plotted against its color or temperature. So those two things, if we plot the brightness of a star versus its temperature, so let's say I saw a star in the sky and I looked at it and I'm like, oh, that's a blue star. And then I get its spectral type and I say, oh, it's a type O because I got its color spectrum. And then I measure its brightness and it turns out to be 10,000 Kelvin. Say, oh, it's up here. It's a blue star, but it's up here in the top left. It's brighter than Rigel. Okay, and so this is a plot of stars, and it's showing you that there's on what's called the main sequence a lot of stars here, all put together. Rigel, Spica, Sirius, the white dwarf that's a companion to Sirius, Betelgeuse, the supergiant, the red giant up there. The sun's here, Alpha Centauri's there, bunch of other stars, Barnard stars down there, and then there's Proxima Centauri, the class M star, very dim red star. Okay, but anyway, what is this HR diagram? It's a plot of brightness versus temperature. So if you measure a star, notice this, if you measure a star and you get its brightness and you get its temperature and you plop it on here, you immediately determine what type it is, what spectral class it is, where it is, and what we'll see is that this determines its evolutionary life, where it's going to end up. Is it going to die as a white dwarf? Is it going to die as something else? What's its size? What's its radius? What's its diameter? What's its mass? All that stuff you can determine from the HR diagram. Here's another HR diagram, another picture of it, and there's your main sequence. Those are all the stars on there. You got red giants up here, supergiants. So if you take a star and you plot it and it shows up there because its color and its brightness, you know it's a red giant. If you plot a star and it shows up here, you know it's on the main sequence. If you plot it here, you know it's on the main sequence. So that tells you a lot about the star and its age and everything. So we're going to learn a lot about that. Okay, the main sequence, all the stars on the main sequence here, every star that's along this line is still burning hydrogen fusion. It's the main thing. Once it stops burning hydrogen, it runs out of fuel. It turns into these red giants and supergiants and eventually white dwarfs. So the main sequence is the period in the life of a star where it's burning hydrogen. Okay, it's like your late 20s, early 30s, early 40s. Okay, you're just sort of coasting through life. Everything should be pretty good at that point. Knock on wood. So it's like midlife for a star, early midlife to midlife. Okay. So there's your OBA fine girl kiss me spectral types. This is the mass relation compared to the sun. So a type O star is going to be 40 times more massive than the sun. A type M star is going to be half the mass of the sun. The brightness here is, thousands of times brighter than the sun. Here, 5% the brightness of a sun. Temperature, 40,000 Kelvin for type O, 3,000 for type M. 20 times bigger than the sun, half the size of the sun. Okay, so full spectrum there along the main sequence. So as we're going down the main sequence here, the stars are getting dimmer and smaller and less massive. Okay, so that's another thing you can learn about the stars. So here's some really big, okay, that's the sun. Here's the orbit of Earth. And here's some giant star, one of the bigger stars, VY Canis Majoris. Okay, and so that dotted line there is the orbit of the Earth around the sun. So if this was the sun, then Earth would be inside the sun. Okay, so that's a little bit crazy to think about. And that will happen someday when the sun swells up to a red giant and we could be engulfed. The sun will not get this big as VY Canis Majoris, but it could easily swell up to big enough to swallow the orbit of the Earth. Okay, so white dwarfs are a type of star that is basically the carcass of a star. So here's Sirius, and there's its little partner here, that white dwarf. So this white dwarf is orbiting Sirius. Sirius is a star, type O. I think it's a type O, can't remember. Is it up here? I don't want to take some time to do that. Anyway, yeah, up here. Sirius, type A. So it's a type A star. Maybe it's type B, I don't know. Sirius, it's type A. Okay, so type A star. So it's brighter and hotter than the sun, but it's got a partner here that's pretty dim. And if you plot that dimness in color, you see that it's a white dwarf. A white dwarf is basically what the sun is going to turn into. Eventually, the sun will run out of fuel, do its thing, and when it dies, it's going to leave behind a white dwarf. Okay, and we'll talk about that later. So a white dwarf, it's a low-mass star, has exhausted all of its fuel. It's the final state of its life. So it's retirement. Basically, when a star retires, it becomes a white dwarf. Okay, that's it. Let's do a summary real quick. Okay, so most stars are small. Few stars are very large. We can measure the masses of the stars using Kepler's laws by watching eclipsing binaries and other stars orbit each other. We can get the diameters of the stars by looking at the light curves, and then when we put it all together, we can put stars on something called an HR diagram, which gives us a hint of which stars are still on the main sequence, which is when they are fusing hydrogen into helium. About 90% of all the stars in our galaxy lie on the main sequence. Only 10% are white dwarfs, and fewer than 1% are red giants or supergiants. This is important because it helps us understand the age of our solar system and our galaxy and the universe itself. Okay, bye.